Hello. We'll begin by flying from the San Francisco Bay Area, where Coursera has its headquarters, to the Caltech campus, where Drugs and the Brain is being taught. In fact, we'll fly to the Kirchhoff building on the Caltech campus, where most of Drugs and the Brain is recorded. Now we'll talk about dose-response relation. The concept of dose and response has intimate connections with the concept of receptors. And receptors and dose-response relations were defined, more than a century ago and many decades before we knew about receptors as proteins and genes. The general idea is that we can add drugs to an organism or to an isolated part of an organism or to a cell in many different ways. Perhaps the most precise way of doing it is the molarity of a drug, its concentration, and we can also express that in terms of grams per liter, grams per hour per kilogram of body weight if we're applying to an entire animal. We can talk in general terms about doses, such as the number of injections, the number of pills, and other way of adding drugs to a system. We can also talk about responses at a lot of levels of analysis. Here is a picture that I showed you a couple of lectures ago about various ways to study the nervous system. We can use all of those ways to study the responses to drugs. And in a more reductionist approach, we can actually measure individual single channels in biological membranes. Unfortunately, we won't have a chance to discuss this in greater detail. Of course, not on here is the classical method of identifying the binding of a drug to its receptor, which is using a radioactively labeled drug or using a fluorescent drug. And also above the level of analysis of this slide is the concept of behavior. We can measure the number of times an animal or a person presses a lever to get a reward, or the ambulation of that animal, or another aspect of the animal's cognitive behavior, such as pressing a lever in a very complex situation in order, again, to get a reward. So these are doses and these are responses, and in a typical, very general dose-response relation, we have a relationship between the drug dose, or the concentration, and the response, and in general, when we have zero dose, we have zero response. And if we do have a baseline response, well, we're just looking at the increment above that baseline. And then when we add enough dose or a high enough concentration, we began to get terms that could be called under various terms no additional response. And sometimes we call this saturation of the response, or a plateau, or a ceiling, or an asymptote. But in general, at some high level of concentration of drug, we get no more response. And so in this case, we can say that the drug is probably an agonist because it is, in fact, eliciting a response. And the term agonist comes from the Greek word to act. And so this is just a fancy way of saying, or an international way of saying, that the drug is acting. Now, we can, of course, do this in a more general. Now let's talk about more general aspects of drug doses. Now let's discuss the so-called infinite sink simplification in Drugs and the Brain. Receptor proteins are numerically scarce in and around cells compared with other protein molecules or with drug molecules in the solution around the receptors. And therefore, drug concentrations are not markedly depleted by binding to receptors. Now, this is very different from elementary chemistry in which one has two reactants reacting with each other, and both of them are depleted by the reaction. Another way of saying this is that drugs remain at constant concentration near receptors, at least on a time scale of seconds to minutes and a distance scale of micrometers. Now, on a longer time scale, of course, the body metabolizes drugs in various organs on a time scale of hours to days. And on a larger length scale, we've discussed about the blood-brain barrier, and we've discussed permeation into various organs. But on the time scale we're discussing here, we can say that drugs remain at a constant concentration near receptors. Therefore, we can use pseudo first-order kinetics, at least from the viewpoint of a receptor, to describe the drug binding. If we have a drug, D, plus a receptor, R, we get a drug-receptor complex. Now, as we'll see, this drug-receptor complex is not what we measure. We measure some downstream consequences of it, usually. But the differential equation for this process is that the rate of change of the drug-receptor complex is equal to a forward binding rate times the concentration of drug times the concentration of receptor minus an unbinding rate times the concentration of the drug-receptor complex. And the key here is that D, the drug concentration, is a constant, not depleted by binding. With that in mind, let's go to a typical drug-receptor modeling scheme. And here's an Excel file, which you can access at Coursera, for a more formal analysis of dose-response relations. Now we have a concentration of agonist and a response. We won't say specifically what response we're using, but it could, for instance, be a number of open channels or the activation of G protein pathway, etc., everything on that first slide. We have linear coordinates in the graph on the left with the yellow background, and we have logarithmic agonist concentration coordinates in the graph on the right. This runs, let's open it up just a little bit and show you that this runs from 1 to 100,000, and we're using, for example, nanomolar here in this hypothetical reaction. So we have a couple of parameters that we can adjust. We have the EC50, this is the half maximal concentration of the drug. We have the efficacy of the drug and the Hill coefficient. Let's see what happens when we make the drug-receptor interaction weaker. We'll change the EC50 from 20 nanomolar to 100 nanomolar. But here, on the linear scale, the response reaches half maximal only toward the end of the range. And here on the log scale, again, the response is half maximal at the EC50. Let's go back to 20 nanomolar for the EC50. And let's go to this very important concept of the Hill coefficient. Now, the Hill coefficient basically describes how cooperative the dose-response relation looks. On linear coordinates, we have more or less a rectangular hyperbola here. We have a linear start and a gradual saturation. On logarithmic coordinates in agonist, we have a different scheme, we have a different form in which there does seem to be a sigmoid plot. Let's see what happens when we make the Hill coefficient 2. What this basically says is that the active state of the receptor is more likely to be associated with the presence of two bound agonist molecules than with the presence of a single bound agonist molecules. And for receptors like channels, which are pseudosymmetric multimers, as we've seen, it often does take more than one bound agonist molecule to activate that receptor. So we'll press return, and now we have a sigmoid start, a parabolic start to the dose-response relation. It looks a little bit like a parabola, and indeed if we blow it up we'll see that it's a perfect square law response as long as we stay at very small agonist concentrations. And the logarithmic dose-response relation has become a bit sharper. Now, another key concept is the efficacy. We're assuming here that every receptor molecule that binds an agonist produces a response. But if we change this so-called efficacy to only half, then the maximum of the dose-response relation never gets bigger than a half, and on either coordinate. So these are examples of dose-response relations involving the concepts of EC50, of efficacy, and of Hill coefficient. Of course, the Hill coefficient is named after A.V. Hill, the great British physiologist. So let's go back to A1 for efficacy. And we will now say in general that if we look at these dose-response relations, again, we have the input parameters. Here's the full Hill equation that we've used. Here is the efficacy, F. Here is the concentration of agonist, the EC50, and N sub H is the Hill coefficient. And so we have the dose-response relation on linear plots here in a light yellow, and on semi-log plots for the agonist in this light red. And the maximal response decreases as the efficacy of the agonist decreases. That is, for efficacies less than 1, the agonist is a partial agonist. And again, for Hill coefficients, there is somewhat of a difference between a Hill coefficient and cooperativity. Cooperativity indicates that after the first agonist is bound, the second is more likely to bind. And that is involved in concepts of shape-shifting proteins, such as we've talked about earlier. The statement that we've made about the Hill coefficient is rather more general than that, and here it is repeated. So let's look at examples of drug classes. If we have a efficacy of 1, we have a full agonist. And here's an example. Nicotine at nicotinic receptors is a rather full agonist, at some nicotinic receptors in the brain. An example of a partial agonist whose efficacy is between 0 and 1 would be varenicline, the drug used for smoking cessation. It also binds to nicotinic receptors, and it's thought that binding to nicotinic receptors but not activating them fully allows varenicline to outcompete nicotine and to give just enough of a feeling of well-being, but not a full activation to help the smoker stop smoking. A good example, now obviously as the efficacy drops more and more, the ligand sits on the receptor and does not allow the conformational change that actually activates the receptor, and that becomes an antagonist against an agonist. An example of an antagonist, switching to another class of drugs, is fluoxetine, which is an excellent high affinity antagonist for the serotonin transporter. Then we have inverse agonists, which actually shift the receptors into a conformation that is not simply inactive, but does not allow the agonist to bind at all. So a different shape entirely. And so an example of a partial inverse agonist is clozapine, the antipsychotic drug, at 5-HT2 receptors. And finally, there are full inverse agonists, which act even more to keep the receptor in a closed conformation, different from the inert conformation. And this would be beta-carboline, which acts on GABA A receptors, and we'll discuss GABA A receptors in a little while.